Let's find the surface area of the portion of the surface of f of xy equals y squared that lies above the triangular region in the xy plane with vertices 0, 0, 0, 3, and 3, 0. Let's begin by sketching just the base region R that has a vertice at 0, 0, one vertex at 0, 0, one at 0, 3, and one at 3, 0. This is a triangular region, and this is the shaded region here is our base region of the three-dimensional surface. And we want to find the area of the surface of the portion that lies above this triangular region. So if you wanted to get a kind of a perspective drawing here, it would be this region in the xy plane, and then you would have a portion of this surface that lies above it. Again, I'm not going to take the time to graph it, but we want to find that portion of the surface that lies above that base region. So let's find, again, recall that the formula for surface area is equal to this double integral r, square root of 1 plus the partial with respect to x squared plus the partial with respect to y squared dA, differential area. So let's find the partial derivative of our original function f sub x, of that function of x and y. We treat x as a variable and y as a constant, and that derivative is going to be 0. And the partial derivative of this function with respect to y, treat y as a variable and anything else as a constant, that partial derivative is 2y. We can go ahead and plug that into our surface area formula. So the surface area is equal to a double integral over the region R of, when we plug that in, 1 plus 0 squared plus 2y squared is the square root of 1 plus 4y squared dA. Now we need to determine the bounds of integration here. Since this isn't a constant, we can't pull it out in front, but we can evaluate this, and we need to determine the bounds of integration. And notice here that the integrand is the square root of 1 plus 4y squared. We can choose dA to be either dy dx or dx dy. Without using advanced integration techniques, if we were to write the order of the differential area dx dy, then we would treat this as a constant. So that's going to be my approach here, is to determine the bounds if we were to write this differential area as dx times dy. If we were to write it in this way, we would treat that as a constant. Otherwise, if the dy was first, we would have to use advanced integration technique, probably trig substitution. So in order to write the order of the differentials as dx dy, the rectangle that we draw has to be a horizontal rectangle. That longest side is our differential x, and that shortest side is your differential y. So our differential area is the long side dx times that short side dy. We need to determine equations for the left x and the right x, and the lower y equals to the upper y equals. Now we do need to find the equation of this line segment that connects these 2 points. The one of the points here, that's the point 3, 0, and this is the point 0, 3. You can find slope between those 2 points. We know the slope is -1, and you know the y-intercept, so you can actually use the equation y equals mx plus b, knowing that the slope of this line is down 3 over 3, which is y equals -1x, and the y-intercept is a +3. Okay, so I'm going to erase this so I can have some space to write out the bounds of integration. Since it is a horizontal rectangle, we need to determine the bounds for x first. We can say our left x equals to our right x equals, and then we would determine the bounds for y, which would be your lower bound for y, or your bottom y equals, to your top upper bound for y equals. Now if we look at the x first, looking at the representative rectangle, the left side of that rectangle, x is equal to 0. To find the right side of that rectangle, we need to find what x equals on this line. So if y is equal to negative x plus 3, we can solve this for x. Solve for x because we're going to need that to determine the upper bound for x. When you solve for x, you can move x to the other side and subtract y. You get x is equal to 3 minus y. So that is going to be our upper bound for x. Our lower bound for x is x equals 0. That's the left side of the rectangle to the right side of the rectangle, x equals 3 minus y. If we slide that rectangle all the way to the bottom, that bottom y is equal to 0, and we slide that all the way to the top, that top y is equal to 3. So our inside bounds of integration, that's since the order of the differentials is dx dy, the inside bounds would be from 0 to 3 minus y, and our outside bounds would be from 0 to 3. Now we have a double integral, and earlier in this chapter we practiced evaluating these. I'd like you to go ahead and try that one on your own. I'm going to skip the steps here and give you the approximate answer. When you evaluate this, this is approximately 10.569. So the surface area of the portion of this surface that lies above the triangular region in the xy plane with those vertices is approximately 10.569. For this next example, we want to find the surface area of the portion of the surface of f of xy equals 9 plus x squared minus y squared that lies within the region R, which is x squared plus y squared is less than or equal to 4. So this is a three-dimensional surface, and we want to look at finding the surface area of the portion that lies within this region, x squared plus y squared is less than or equal to 4. So let's look at the graph of just the base region. If you're looking at x squared plus y squared is less than or equal to 4, you're looking at a circle with radius of 2 and centered at the origin. So this is our base region. We have this surface in space, and we want to find the portion of the surface that lies above that base region. In 3 dimensions, we have some kind of surface up here. It looks like it has a saddle point, but we have some kind of wavy kind of surface up here. And this is the portion in the xy plane that lies above that. So it is this portion of the surface here that lies above this base region. And recall the formula for surface area is a double integral r, square root of 1 plus that partial with respect to x squared plus that partial with respect to y times that differential area dA. Let's find the partial derivative of the function with respect to x. Go to the surface itself. F of xy equals 9 plus x squared minus y squared. The partial derivative with respect to x, you treat x as a variable and y as a constant. That derivative is 2x. You take the partial derivative with respect to y, treat y as a variable and x as a constant, and that partial derivative is negative 2y. Let's go ahead and plug it into the formula for surface area, a double integral of the square root of 1 plus, if we take this and square it, we get 4x squared, and we take this and square it, and we get 4y squared, times the differential area. So now we have this double integral. We want to determine our bounds of integration as well as the order of the differentials. We can use dy dx or dx dy here. However, in both cases, that's going to present some challenges. So what we're going to do here is use polar coordinates and use conversion equations so we can determine we can evaluate this integral. Now, since we're using polar, remember that dA in polar is equal to r times dr times d theta, or we can write it as r times d theta times dr. So in either case, we want to determine the bounds of integration. We need to find our bounds for r and our bounds for theta. Go ahead and erase this portion here and look at our bounds for r. If we were to slice this like a pie, we see that it's r simple. But we can also slice this using concentric circles, and it's theta simple. So we can determine our bounds for r. We can determine the inside r, the smallest radius of any slice here. That smallest radius is going to be 0. And the outside radius, that largest radius, is the radius equals 2. Your upper bound and lower bound. Your lower bound is 0, your upper bound is 2. To find your bounds for theta, we want our smallest angle, and we'll start here at theta equals 0 and determine the upper bound, that largest angle theta, that would give you the entire region. In this case, that would be 2 pi. So we have our bounds of integration. But we also want to make some substitutions here. If our differentials are dr and d theta, then we can't have any x's and y's in here. So one of the conversion equations that we use in converting is x squared plus y squared is equal to r squared. And notice that we have actually 4x squared plus 4y squared. That would have to equal 4r squared. So when we make the conversions here, it's going to be our double integral of 1 plus 4r squared, and then it's going to be r times either dr d theta or d theta dr. What you can do here, I would possibly choose d theta dr. That way when you do the inside integral, you can treat r as a constant and integrate with respect to theta. You could also do in this order, but then you would use substitution to begin with in the inside integral. Since I've chosen this order, d theta dr, we want to determine our bounds for theta. That's our inside bounds, go from 0 to 2 pi. And our outside bounds for radius r, it goes from 0 to 2. All right, now we've already practiced evaluating these double integrals in previous sections, so without going into that, I'll give you the answer as approximately 36.2 if you were to work that out. So what that means is the surface area, the portion of this function that lies within that region, x squared plus y squared is less than or equal to 4, that surface area is approximately 36.2.